one. So because this chapter 36, has a lot of suggested problems, and actually it has material that we distribute over 2 weeks, the recitation, 1 hour recitation, is not going to be enough. So I wanted to prepare some videos that you could watch before coming to recitation, and then we can perhaps discuss the solutions. So this is the first of those videos. Hopefully there will be a second one. And for this one, I'm going to go over the warm-up problems that I suggested on audio class. So this is they're all from our textbook from Giancoli, the problems 2, 4, 11, 19, 24, 28, and 71. Unfortunately, I could not acquire the equipment I was hoping, so I will be solving this on my whiteboard, but hopefully this will be fine. So before I put this online, I will be putting the problems under the video, so you can read them. So the first one is problem 2. Here we have a certain type of elementary particle that travels at a speed of 2.70 times 10 to 8 meters per second, a considerable fraction of speed of light. At this speed, the average lifetime is measured to be 4.76 times 10 to minus 6 seconds. What is the particle's lifetime at rest? Right. So this is somewhat straightforward, but still I want to emphasize the basic principles that we are going to deploy here. So the velocity of the particle is 2.7 times 10 to the 8 meters per second. Now recall that c is about 3 times 10 to the 8 meters per second. So the way I remember this is 300,000 kilometers per second, and it comes to 300 million meters per second. So v over c here is 2.7 by 3, so that's 27 by 30, that's like 9/10. So it's 90% of the speed of light. It's quite a bit. And we are given the lifetime of the particle, and this is going to be 476 times 10 to minus 6 seconds. Okay? And the question is asking, what is the particle's lifetime at rest? So this is the observed lifetime. Now this is something you could just make an analogy with the muon decay experiment, and you can say that in that experiment the muon's lifetime increases in the laboratory frame with respect to their rest frames. On the rest frame, where the muons are moving at very slow speeds with respect to laboratory, their measured lifetime is very short. But when they're moving at high speeds, at speeds comparable to speed of light, then there is a measurable increase in their lifetime. They travel distances that they wouldn't be able to travel if they lived really that short in the laboratory frame. So this is the extended lifetime, right? And this is connected to the actual rest lifetime of the muons through time dilation formula. Now, time dilation formula is delta t naught by 1 minus v square by c square. Now, is this applicable here? The answer is yes. So time dilation is applicable when one of the observers is actually measuring proper time. And proper time is defined as, between two events, is defined as when the two events are taking place at the same location for a particular observer. And for this particle in question here, the lifetime that's measured is proper time, right? So the formation of the particle and the decay of the particle, these are the two events. The time between them is measured as proper time by the particle itself, because it takes place at the same location, right? Namely, the location of the particle, so just right where the particle is. So that is what is observed by the particle, and it's going to be something short, and the observed lifetime is going to be given by this formula here, by the time dilation formula, and it's longer than this delta t naught, the proper time. Now, how do I know it's longer? Because this is a number, this v square by c square is a number between 0 and 1. I subtract this off from 1, it's going to be between 0 and 1. Taking square root still keeps it between 0 and 1. So when I move it to, if I take the reciprocal of this, when I move it from denominator to numerator, it's going to be something larger than 1. So this delta t is going to be larger than delta t 0. Right? And that is going to be, this is the observed lifetime, but what we are looking for is delta t 0. So that's going to be 1 minus v square by c square times delta t. Right, so if this is the lab lifetime, this is going to be the rest frame lifetime. And I'm not going to carry out the algebra, but it's trivial actually. When you go through this, I think you find something like 2.075 times 10 to minus 6. So because this is quite close to C, that factor is considerable, right? So it shifts by something like quite a bit, yeah. Maybe a factor of 2 or so. Okay, so this is problem 2. As I said, this is a somewhat straightforward application of time dilation, but you need to see that time dilation is actually applicable. And this you can do either by analogy with the muon experiment, or by thinking that whether one of the observers is measuring proper time. In this case, the answer is yes. The particle itself is measuring the proper time, right? And this is how you set things in this formula, right? This delta T naught is the rest lifetime, which is what we are seeking, and the other one is the dilated time, the time that experienced time dilation. Okay, next one is 4. So let me go over here. If you were to travel to a star 135 light years from Earth at a speed of 2.8 times 10 to the 8 meters per second, what would you measure this distance to be? Okay. So we are at Earth, and there's a star that is 135 light years away. Years, and your speed is 2.8 times 10 to the 8 meters per second. So we are moving, we are trying to go to the star with some speed, again a considerable fraction of speed of light, right? What would you measure this distance to be? Okay, so there are a number of assumptions that we need to make here to be able to solve this problem. So first of all, this 135 light years is measured in some reference frame. Now, it's reasonable to assume that this is the reference frame of Earth, but then for this to make sense, you need to be able to make a simultaneous measurement of the position of the star and Earth. So we are going to assume that the star is at rest with respect to Earth, right? This is not given in the problem, but without this assumption, it just becomes too hairy. It's very hard to solve. You need to make another assumption. Without making any assumption, it's impossible to solve. And this is the simplest assumption we can make, and it doesn't actually make this trivial. So that's a reasonable assumption. Sometimes assumption will make the problem trivial. Then you should not make that assumption. But here, this is reasonable. So the assumption we are making is that this 135 light years is measured in the rest frame of Earth, and the rest frame of Earth is also the rest frame of the star that we are trying to go to. Right? So we are moving with respect to Earth at this speed, and because of this, so we are moving that way. What we are going to see is that we are just sitting in our spaceship here, and Earth and the star are moving. Actually, this whole thing is moving with this speed towards us, right? So Earth is going to pass by us, and then after some time passes, this star is going to pass by us. But this whole thing, because it is moving with respect to us, is going to experience length contraction, right? It's going to get shorter. So that length contraction is going to be, again, 1 minus v square by c square times L0. And this L0 here is the length that is measured in the rest frame of the object in consideration. So here the object in consideration is this whole Earth-star system. We assume they are at rest with respect to each other, so we can actually make a meaningful measurement of the distance between them. And that length is 135 light years. Right? And that is going to get contracted in our reference frame because we are moving with this speed. Right? So 135 light years. And you need to calculate this. Did I make this calculation? Actually, no. But this is something more or less trivial. So again, this is quite high. So I would expect something like a factor of 2-3 at least of contraction. And so this is going to reduce So if you find something larger than 135, you're making a mistake, right? That's one thing. This is a number between 0 and 1. This is a number between 0 and 1. The square root is something between 0 and 1. That number should get smaller. You should feel contraction, right? Okay, but I'm not going to make the further calculation. I'm not going to calculate things. So in such problems, especially since we are dealing with astronomical distances, it is okay to leave things in light years. Right? Now here they're not asking you in what units to give the answer, and it is perfectly okay. But if this is a computational problem in the exam, the safest thing is to go to MKS units, so to go to meters. Right? That's one recommendation I would like to make here. Okay, so the next one is 11. At what speed do the relativistic formulas for length and time intervals differ from classical values by 1%? And they note that this is a reasonable way to estimate when to do relativistic calculations rather than classical. So if the correction is less than 1%, you don't need to bother with it. So we are going to calculate some velocities here where the corrections are of order 1%. And if you're moving slower than this, you might as well use the classical formula unless you want to be more accurate than 1%. Now sometimes you need to be, sometimes you don't need to be. It depends on the situation. But theoretically, your tolerance could be much less than 1%. This is a rule of thumb, but whether it's applicable or not depends on the situation. So we want, for A, we want the length formula. So this is length contraction. This is L1 minus V square by C square L naught. Right, so this is the contracted length. This is the proper length in the rest frame of the object, the length of the object measured in the rest frame of the object. And this is the contracted length as measured by a moving observer, an observer moving with V with respect to the object. Okay, so we want this to differ from the original by 1%. This is going to decrease. Right, this is a number less than 1. So this is going to be, at the limit of 1%, it's going to be 0.99, 1% less than 0. Now for part B, they're asking for the change in the time interval, time dilation. So delta t is going to be delta t naught, the proper time measured between two events, divided by this so-called gamma factor or Lorentz factor, say. And this is going to increase, so this is going to be equal to 1% larger than the proper time. And you need to carry out the calculation and find V in both cases. And to first order, these are actually going to be the same. Let me demonstrate that. And then by making another substitution, you can actually see which one is bigger, which one is smaller. But let us set this equal to each other. So 1 minus V square by C square is equal to 1 minus 0.01. Now I'm going to make binomial expansion for this. So binomial expansion, which we are going to use for another problem. Thanks. So if I add a small number to 1 and take the nth power of this sum, to first order in x, to first order in this small number that I'm adding, the answer is going to be 1 plus n times x, the exponent. So this exponent, I wrote n, but doesn't need to be an integer or anything like that. It can be anything. It should not depend on x, though. It can't be something like 1 over x, then things change. The answer is going to be just 1 plus nx. Right? And this comes from the Taylor expansion. You just take this, you Taylor expand this, and this is the first term. So the second term here is going to be something like n times n minus 1 divided by 2x squared, and then it's going to be n times n minus 1, n minus 2 divided by 3 factorial times x cubed, and so on and so forth. Just Taylor expansion, or binomial expansion in this case. Right? So because x is small, we drop those x squared, x cubed, x to the fourth terms because they are even smaller than x, but we keep this term. Right? So if you do this, if you apply this to this, so I'm going to assume v over c is small, so v squared by c squared is even smaller. this becomes 1 minus a half v square by c square is 1 minus 0.01. So v square by c square is 0.02. Right? And then you can solve for this. So this is for this one. This is for part A. Now for part B, we get something a little bit different. 1 over 1 minus v square by c square is 1 plus 0.01. Okay? And if I apply the binomial expansion to this, now the exponent is not a half, but minus a half. So this minus cancels that minus. This becomes 1 plus a half v square by c square is equal to 1 plus 0.01. You again get the same relationship. V square by c square is 0.02. Okay? So to this order, to first order in v square by c square, they actually give the same answer. But if you go to the higher order, and how do you do this? You just solve this exactly, right? So instead of doing this, let me get some room here. What you do is you get 1 minus v square by c square is 0.99 squared, and then move this to the other side. 1 minus 0.99 square is v square by c square, and well, you're going to get something slightly different than 0.02. And then if you take the square root of that for the first one, I didn't check my algebra, but I got something. So this gives, when you do this honestly, 0.1410 something something. And if we carry out the same thing here, you just square both sides and then move things around and take the square root and so on and so forth. This one gives 0.1403. And so on. As you see, they're very close. They differ by by a factor of 7 in 1400, right? So it's less than 2%, something like that. Less than 0.5%, sorry, less than 0.5%, the difference, or about 0.5%, I should say. Yeah. So to the first order, they are the same, but around these values, when your b over c is 14% or so, the error you're making, the difference you obtain for the length and for the time interval is about 1%. So if you're moving slower than 14% of speed of light, then and if your tolerance is about 1%, you might as well use the classical formulas. That's the conclusion. Okay, so the next one is 19. Let's see that. Alright, so this one is about Lorentz transformations now. Let me erase this. Okay, an observer on Earth sees an alien vessel approach at a speed of 0.60 c. The Enterprise comes to the rescue, and there's a figure overtaking the aliens while moving directly toward Earth at a speed of 0.90 c relative to Earth. What is the relative speed of one vessel as seen by the other? Yeah, so let me try to reproduce the figure here. This is Earth. There is an alien vessel here. Let's call them Zindi. Right, this is moving with respect to Earth at 0.6 c, and we have USS Enterprise. Right, and this is moving with respect to Earth at 0.9 c. Right, so Enterprise. And they're asking what is the relative velocity of these two with respect to each other. The relative velocity of Enterprise with respect to the aliens, or the relative velocity of the aliens with respect to Enterprise. Obviously, they should be equal and opposite to each other. Okay? Now, this is an application of the transformation of velocities or velocity addition formula. So let me just copy that formula. I have it here. So this is ux is ux prime plus v by 1 plus v times ux prime by c squared. Okay, so this v, so we have two reference frames. One is the primed reference frame, the other one is the unprimed reference frame. The primed one, so this is the standard configuration. This is figure 11, I think, in the book. So you might want to look it up to see what I'm talking about, but I'm going to draw it. No, let me actually just draw it. So I have two reference frames. Okay. So we'll call this S prime. We'll call this S. So this is X. This is X prime. Right, this is the primed one. This one is moving with respect to S in the positive x direction with velocity v, and the origins of these two reference frames, these two coordinate systems, actually coincided at t equals t naught equals t equals t prime equals 0. Okay? So that's the standard configuration, but this one is moving in positive x direction with velocity v. So this ux is the velocity of x component of the velocity of some object as measured in S coordinate system, S reference frame. Ux prime is the x component of the velocity of the same object as measured in the S prime reference frame. Right? So we are trying to calculate the velocity, the relative velocity of these two. So we want to actually make one of these the unprimed coordinate system and make the object move there, right? And see if this works out. So one way to go about this is there are two ways. I'll show them both. Is to set this up like that, right? So I have a unprimed coordinate system here, x fixed to enterprise, and the prime coordinate system is going to be at Earth, right? So this ux is then going to be the velocity of the Zindi vessel with respect to enterprise, the velocity of this vessel as measured in the unprimed coordinate system, right? And if I can write everything else, then I'm going to be fine. So let me erase this. I need the space. So ux, and I'm going to assume that this is just the x-axis for both of them, right? I'm not going to clutter everything here. So ux is the speed, velocity, or x component of velocity of Zindi with respect to enterprise. Okay, ux prime is the x component of velocity of Zindi. It's the same object we are talking about, but now in the prime coordinate system with respect to Earth. And v is the velocity of the primed coordinate system with respect to the unprimed one, velocity of the x component, or just the velocity, let's say, velocity of Earth with respect to enterprise. Okay, so do I know these numbers? Here, ux prime is going to be the velocity of the Zindi vessel with respect to Earth. So as measured here, they are moving in negative x direction with a speed of 0.6 c. This is going to be minus 0.6 c. The velocity v is going to be velocity of the Earth with respect to enterprise. So enterprise at rest in their own reference frame. Earth is moving in this direction, which is the positive x direction, at 0.9 c. So this is positive 0.9 c. And the answer we are seeking, x prime, is going to be minus 0.6 c plus 0.9 c divided by 1 plus minus 0.6 times 0.9. Okay? C square by c square. So c square, they go away. Okay, so this is 0.3 c divided by 1 minus this thing here. 0.3 c divided by 1 minus, this is 54, 0.54. And I'm not going to calculate, but this is easily doable with the calculator. Okay? Now, so this is one choice. There's another choice you can make. You can calculate. So with this choice, the number we were calculating was the relative velocity of the alien vessel with respect to enterprise. We could also make the opposite choice. We could choose this as our unprimed coordinate system. things. And we will still keep this as our prime coordinate system. Okay? And now we are going to be measuring the velocity of enterprise in these two. Okay? So this is still x prime, and this is still s prime. Now here, I'll try to fit things here, but for that I need to erase this formula, just to see if we are getting a sensible answer this way as well. So ux, this is the velocity of the object in question, here enterprise, in the primed coordinate system, right? So velocity of, I mean, it's actually the x component of the velocity of enterprise with respect to Zindi, the aliens, right? So ux prime is the velocity of enterprise, right? It's the same object, but in a different coordinate system, a prime coordinate system with respect to Earth. And this v is the velocity of the primed coordinate system with respect to the unprimed coordinate system. So this is the velocity of Earth with respect to Zindi. Okay. Now again, if we put the numbers in, we can actually calculate all of this. So ux is what we are looking for. There is no trying here. So ux is what we are looking for. That's just ux prime, Let's write this down. Plus v by 1 plus ux prime v by c squared. So ux prime is velocity of the enterprise with respect to Earth. So velocity of the enterprise with respect to Earth is in the negative x prime direction, right? And it's at 0.9 c. So this is minus 0.9 c. And v is a velocity of Earth with respect to the Zindi that is going this way. It's in the positive x direction, and it's 0.6 c. So it's 0.6 c. And again, if you plug numbers in the numerator, you're going to get a minus 0.3 c. So ux is going to be 0.3 c divided by 1 minus the product of this, which we already did here, 0.54. And as expected, so this is minus, right? As expected, this is equal and opposite to what we calculated there. So the velocity of the enterprise with respect to Zindi is equal and opposite to the velocity of the Zindi with respect to enterprise. Like, you can do this either way. Now, the trick here is to setting these up, right? And the way I set this up was that I thought about, so what are they asking? They're asking about relative velocity. So this relative velocity can be expressed as the velocity of one of the objects with respect to the other. So I need to fix the unprimed coordinate in one of the objects, and the velocities that I'm measuring, the u's in my velocity transformation formula is the other object, right? Once I set it up this way, then you can apply the velocity transformation formula. Though if you just try to do this randomly, there is a high chance that you're going to get this wrong, right? So you can guess what is going to happen in the top part, right? Because this, you know that the denominator is actually the relativistic correction. The numerator is the Keplerian Galilean transformation value, and the Galilean transformation here will give 0.3 c or minus 0.3 c. So this is something you could guess, but in the denominator, is there a minus or a plus here? Right. So that's you shouldn't do this with guesswork, but instead really write things formally and apply it this way. Okay? And this should become more or less automatic. Because this is not a very challenging question. This kind of velocity transformation can easily be made part of a more complicated question. Yeah. I'm not saying I will do that, but you should be ready to encounter questions like that. Okay. So the next one is 24, I think. Yeah. So we have a reference frame S prime that moves at the speed of 0.92 c in the positive x direction with respect to reference frame s. The origin of s, okay, so this is the standard configuration where the velocity is 0.92 c. An object is stationary in s prime at position x prime equals 100 meters. What is the position of the object in s when the clock in s reads 1 microseconds according to the Galilean and Lorentz transformation equations? Okay. Where did I put my... Okay, so this is one of those questions that you might have a tendency to solve with length contraction or time dilation or with some weird combination of those. But yeah, it's like you can do it that way, but it's going to be very, very complicated and you can easily go wrong. Okay. So this really requires Lorentz transformations. This is question 24. We have this standard configuration. Let me switch to black again. We have the standard configuration of two reference frames. S prime with the prime coordinate here, S with the unprimed coordinate here. This is moving some velocity, 0.92 c in the positive x direction, and their origins had coincided when both clocks showed 0. And the x's are parallel and so on and so forth. And so we have an object that's stationary in S. So its reference frame is in S prime. So its reference frame is really S prime. At position x prime equals 100 meters. So x prime is equals 100 meters. What's the position of the object in S when the clock in S reads 1 microseconds? Sorry, it's nanoseconds. Is it? No, it's microseconds. Yeah. Okay. So t is 1 microsecond, so 10 to minus 6 seconds. All right, it's milli, micro, nano. This is 10 to minus 6 seconds. And they're asking what's the position at this time, right? That is x here. Okay, so this is always correct, right? So x prime, because it is stationary in this reference frame, x prime is always going to be 100 meters. At equals 0, it equals 1 microsecond, at equals milli microseconds, doesn't matter. But this x is going to change. So at equals 0, it is going to be somewhere around this. Let's discuss that, whether it's exactly this or not later. And then it's going to just keep increasing. Right? So in the Galilean transformations, if this was just Galilean physics, if the speed of light was infinite, or if we didn't know about Lorentz transformations, we would say that at t equals 0, this thing is at 100 meters. In 1 microsecond, it moves by this velocity times this t, and it will be 100 meters plus this t times that velocity. Right. So for the Galilean part, the x at t equals 1 microseconds would be this x prime plus v times t. Right. So I don't like actually using this notation because this t is actually a delta t. It's the t that's given minus our reference time, which is t equals 0. But the book uses this notation, so I'm going to stick to that notation. But Galilean transformation is just 100 meters times something, right? So it's 100 plus 0.92 c times 1 microsecond, right? Whatever this is. I think it's small. It's something small. So this is. Let's calculate it. This is my. So this is 0.92 times 3 times 10 to the minus 8 times 10 to the minus 6, 10 to the 8, sorry, 10 to the minus 6. This is going to be 100 plus 0.92 times 3 times 100. So this is going to be 100 plus This seems too much. Okay. 27.6, right? 376. My algebra might be wrong. My algebra might be off, though. I don't see how. This is what you get, right? Anyway, so for the Lorentzian situation, what we need to do is to apply Lorentz transformations, right? So what will be this position x when t is at a certain value, t prime is at a certain value, and so on and so forth. So here I looked up the formula from the book. This is gamma times x prime plus v t prime, right? Okay, this is fine. I know x prime. X prime is 100 meters, regardless of the time that I'm measuring this. This t prime, however, I do not know, right? And that t prime is not 1 microsecond. It's going to be something different, and that t prime is actually related to t through this Lorentz transformation plus vx prime by c square. So we have the forward Lorentz transformation in some of the books. Actually, I uploaded a section on for carrying to class. I think that includes the backward Lorentz transformation as well. So you can get also expressions from elsewhere of t prime in terms of t, but it's not very hard to invert this. So let's do that. We are going to move gamma to denominator, move this to the other side. So t prime is going to be t over gamma minus vx prime by c square. Right now we can put this in there. I will erase this. This is just standard configuration. Nothing complicated here. So x is going to be gamma x prime plus v, what is t prime, t over gamma minus vx prime by c squared. So let's go through this. This is going to be gamma x prime plus vt minus gamma x prime v square by c square. Okay? So I can do this, gamma x prime 1 minus v square by c square plus omega t, and this is 1 over 1 minus v square by square root, so that partially cancels this one. This is going to be x prime by gamma plus vt. Right, so compare this to this. Now it's not trivial to see that this is what will come out, but I'm sure you can make some argument. With the length contraction and time dilation to see that this is the answer. Right. So let's go back to these reference frames. S prime and s, and we have an object that is at 100 over here. So you might argue that this object is going to move a little bit forward by v times t, and then this whole this whole distance is going to get contracted, right? And this is exactly what's happening. The distance is getting contracted and it moves forward by v times t. But it's easy to see this after doing it, right? It's very easy to make an incorrect argument by, for example, trying to transform time as well, and so on and so forth. So as I said, this is something you can, in principle, do with length contraction and time dilation, but it's not something I would recommend. Right? Now, to be sure, if you're very confident of yourself, you can say that what is happening here is that this thing actually it is moving with some velocity, so it starts at a point that's contracted by length contraction, so it's not at 100 meters but 100 meters times the Lorentz factor, and then it is moving at some speed, the 0.92 speed of light. It's for some time t, 1 microsecond, so it's going to be that contracted length plus the distance it traveled. So you could say that, but as I said, my recommendation is to actually go through this calculation formally. I mean, in the exam, at least, you will have ample time, and there is no need to try to take shortcuts. Right? And again, this should be automatic. Applying these Lorentz transformations this way should become more or less automatic, because this can, again, easily be made into a part of a much more complicated question. All right, 24, and then 28. Let's look at that one. Okay, if a particle moves in the xy plane of system S, figure 11 is the standard configuration figure, with speed u in a direction that makes an angle theta with the x-axis, show that it makes an angle theta prime in S prime given by tangent theta prime is equal to sine theta times square root of 1 minus v squared by c squared divided by some expression. Okay, just no point in reading. You'll see it on your boards video. Okay, I'm not going to solve this in full. I'm going to show how to solve it. This is an example of a straightforward but tedious question, and I don't want to go through the details. I mean, you can see the full solution in the solution manual that I posted on OptiClass, but I will give you the idea of how to set this up. So this is question 28, and I have these two reference frames in the standard configuration. S prime is moving with some velocity v, and S. Okay, so they're telling us a particle moves in the xy plane of the system S with a speed u in a direction that makes an angle theta with the x-axis. Okay, so let's also call these axis y prime. Okay, we have some particle that moves with some velocity u, and that velocity makes an angle theta with the x-axis. This is the idea. Okay. I can probably make this bigger. There's no need to make it so small. Okay. So the particle's velocity looks like this reference frame, and that velocity makes an angle theta. X, this is y, this is x. Okay. Now, obviously, this is going to have two components of that velocity. So there's going to be a ux and a uy. Yeah. I'm not putting the arrows there because they're components. They're not actually actual vectors, but sometimes some books put actually arrows on the components as well, so that's fine. But I'm referring to the signed distances here. Okay, now in the primed coordinate system, with respect to S prime, this particle is going to have another velocity. The velocities are going to get transformed, and that velocity is going to look like so. Because the particle is the coordinate system is moving that way, the particle is going to be moving at a slightly less velocity in the x direction. Let's say it could be, of course, a lot less velocity, but I'm just going to assume it's slightly less velocity, right? Prime. And the y components are not the same, right? Just it might look the same, but they're not. Okay, and then we need to figure out what this theta is. In fact, what this tangent theta is, what the tangent of this angle is, right? So they're giving some expression and ask us to show that this is true. So tangent theta prime is going to be just the y component of the primed velocity and x component of the primed velocity, right? And these you can look up. You can look up from the book that you're going to have some expression. There is going to be some cancellation. There are some common factors, and then you need to write the two factors in terms of each other. So there's a sine theta and cosine theta. So I suspect there is a u times, so ux is going to be u times sine theta, uy is going to be u times cosine theta. So you need to use these two identities as well, which you probably remember from Physics 105 or from calculus. And then you write these expressions, you plug these things in, and you're going to get the expression there. As I said, this is straightforward but tedious, and I don't want to go through this. But if you have any problems, by all means, we can discuss it during the recitation. But I'm not going to actually make the calculation. First, try to do it yourselves, and then try to look at the solution on AutoClass from the solution manual. If it still doesn't make sense, by all means, ask me. Okay, the last one is 71. So we have an airplane that travels at 1300 kilometers per hour around the Earth in a circle of radius essentially equal to that of the Earth, returning to the same place. So it just makes a round trip and comes around. Using special relativity, estimate the difference in time to make the trip as seen by Earth and airplane observers. Okay, so this is something, and they say hint use the binomial expansion. So let's first write down binomial expansion. 1 plus x to n is approximately 1 plus an x for the case when absolute value of x is much smaller than 1. Yeah. So a small x, as we say sometimes. So this is a situation similar to, so this is time dilation, first of all, right? And the rule of thumb for using time dilation is that one of the observers should be using proper time, where two events take place at the same location. Now, on the face of it, it looks like for both observers, the two events, the departure of the plane and the arrival of the plane, takes place at the same location, right? Let's say this is some airport on Earth. For Earth's reference frame, it takes place at the same location, it's the same airport. For airplane's reference frame, it's going to look like that they are taking off where they are and they are landing where they are. Okay, so it looks like they are both measuring proper time, and this is what leads to, of course, the twin paradox. But the resolution of the twin paradox is that one of these observers' calculations are invalid because they are not actually in the same reference frame. They are changing reference frames. And this airplane must be changing reference frames because they are first going in one direction and then in the other direction, right? So they're first getting farther and they're getting closer. So they must be reverting their velocity, which means they must be changing reference frames. So their calculations are not valid. They are not in an inertial reference frame. And the observer on Earth is in an inertial reference frame. They actually measure the proper time. Okay, so they, if you look at this delta t, equals delta t naught by 1 minus v square by c square. Earth is measuring delta t naught. So less time is going to elapse on the airplane. If you actually took an atomic clock on the airplane, you would actually be able to measure this, though there is a complication that I will mention at the end. Okay, so we resolved which one is measuring the proper time, and that proper time is easily calculated. So delta t0, the time it takes for this trip, is the distance that's traveled divided by the velocity of the object that traveled the distance. So that's going to be delta x by v, and this delta x is going to be 2 pi r, where r is the radius of Earth, divided by the speed of the plane. Yeah. So this is the circumference of Earth divided by velocity. Now the other observer, the observer on the plane, is going to measure dilated time. They're going to experience time dilation. They're going to measure less time has passed. By how much less? By this much less. So we need to calculate this by binomial expansion. So that's going to be 1 minus v square by c square, minus a half. And I did actually calculate this, I think. Oh no, I didn't calculate this. I didn't calculate this, but so okay. So this becomes 1 plus a half v square by c square. So the time difference, delta t or delta t naught minus delta t is going to be this whole thing, 2 pi r by v times this factor, a half v square by c square. This is the time difference, and I looked this up. I didn't calculate it, but I looked it up. It's about 8 times 10 to minus 8 seconds. Right. Now, this is something measurable by today's technology. Right. First of all, you can do this trip many, many times. Right. You put a clock on. Well, you give a bunch of clocks to an airplane pilot friends of yours, and they are going to just fly between Ankara and Istanbul many, many times. Well, not during this time, but another year. And over the course of a year or so, this time difference that's accumulated is going to be more than the average drift of let's say 10 wrist clocks. But this is not going to work because there is an additional effect that the gravitational field is different on the surface of Earth and at the altitude that the plane is flying, and that leads to an additional time shift, and that time shift is actually more important than this one. And so it depends on the speed of the plane, of course. Maybe this is too high for this to be, but I think that, for example, 500 kilometers per hour, that effect is more important. The cruising altitude difference in gravitational field leads to an additional shift in the time, and that actually dominates. For example, that's the dominant effect for the GPS satellites, which are going in free fall orbits around Earth. So they are moving at quite high speeds, but the effect is dominated by the gravitational effects. But anyways, this is the answer that comes out. It's something small but measurable, certainly by atomic clocks. But even if you get 10 times this effect or so, you can measure it by combining a number of wristwatches, I think. A microsecond is, I think, achievable. Picosecond, no, but nanosecond, no, but microsecond is achievable. So 10 times this is like a microsecond. Okay, so that's all I want to say for this part, and I'll try to prepare a second part hopefully soon.